Hello, everyone. Thank you for joining this presentation. I'm very happy to share a little bit of the work we've been doing with this community. My name is Ju. I'm a simulation engineer at Novelis, which is a leading producer of rolled aluminum and the global leader in aluminum recycling. I won't be too extensive on the company profile, but just dive right into what we brought for this presentation. And today I'll be talking about Ego Simulate. I'll provide you with a comprehensive overview of its purpose and the significant benefits we've been deriving from this framework. So I'll start off with an overview of the framework, give you guys shine the lights a little bit on a use case and taking any questions if there's any. So what is Ego Simulate? It's a foundational project from our group, and we aim here to try simplify the simulation development lifecycle. And what we're proposing here are standard modeling practices to make it more efficient, but also consistent. And we're designing this solution to be scalable as well by modularizing the processes and try breaking them down into more manageable parts. A key aspect of this project of Ego Simulate is the creation of data-driven simulations only for the data layer. And maybe it's a little bit not so clear just with this single sentence, but I'll be talking more in detail about this in the further slides. And on top of the simulation framework, it's not only a simulation framework, but a whole platform, right? We plan also to have an optimization layer to further streamline the process. As our final solution, we envision to have a self-service aluminum plant simulation platform where a user that doesn't have so much knowledge in AnyLogic or simulation itself could build their own plant, their own aluminum plant from scratch. So there's a lot of work we already did on the modeling side. So in the AnyLogic side, building this generic model that we're working on, creating the infrastructure in the model for to pretty much create models, right? Different models from a person in the platform. And we have built a custom aluminum library that is needed to do a representation of this plant. Also, high-level components that we've been working for the structure of this generic model. How do we instantiate things programmatically, but also schedulers? How do we start from a given point in the plant and not always from the very beginning of the process? So different components that are needed to have a fully functional plant. And we have been having a lot of brainstorms and discussions on how do we envision the user experience to be in this platform. We don't have anything solid yet where we created a specific platform for Ego Simulate, but we are about to start that. At this moment, we are mostly conceptualizing, thinking of different ways we could provide this experience to the users. And although there is a lot of work that has already been done in the interface side of things that we use for other use cases, but we don't have actual platform yet. So that's where we are at right now with this with Ego Simulate. And to give a picture of the framework architecture currently in place, this is what we have. And this has been used for different use cases, where we have here central to this framework deploy AnyLogic model that reads data from an SQL server, but also outputs data for the same SQL server database. We also have this user interface, which I will also talk a little bit further on it on later slides. But this is the main place where a user could manage their scenarios, edit them, view, but also create new scenarios. They could see the model from it. They could also navigate through the model from it and access reports from it. So we in this framework, we envision to be a single platform where a user can do everything related to their model on it. And as mentioned, we built a custom library, and this short video is going to just demo real quick what kind of elements we have encapsulated, what objects. So there are very specific machines in the aluminum industry we have encapsulated with like mills, furnaces, and different vehicles that we use, and storage spaces and other connector objects we have. And in the classic way, you could just drag and drop in the panel and just use them, right? By setting all of the different parameters associated to each one of them, like changeovers, how does metal is lost by each one of these assets, availability. So we exposed all of that and made very configurable. Now it's in this video, it's just showing an example of a plant, right? Like that could be built on top of using this library with a simple visual representation using space markups and so forth. So this only shows the capability of what we have right now on the library, right? But as mentioned earlier, we're trying to envision a low-code platform in the end. So we want to have a self-service platform with pretty much no-code to low-code platform where any user could build their simulation model without the need of an expert. But this wouldn't mean the substitution of an expert, because still for more complex models, there would be needed, more detailed logics and rules and different ways we need to set up the model than an expert would be necessary. But the solution aims essentially to make simulation more accessible to everyone in Novelis. And I think that's one of the things in simulation modeling. The learning curve can be pretty steep. It's not a tool or technology that people know so much. So one of the goals here is to make it more accessible. Now with this library we have enhanced, the other question that comes into mind is how can we make it low code, right? How can someone build a simulation model without having knowledge in AnyLogic or even opening it? So for that, our idea here is to build, and we're working on a generic model with the infrastructure to programmatically instantiate objects, to initialize the model only from the data layer. So from the data provided, the model would initialize itself and create those objects and in the very beginning of it without any of the drag and drop. So that's the challenge we have here. Now, how can we build the structures for this programmatic instantiation? I think some might be already aware, but every single object in AnyLogic can be translated in their compile code to a given constructor that we can learn from it. What needs to be specified and what kind of arguments are necessary to create this object. And then from this, by learning this, we can create an infrastructure in the main agent, right? To add them to a level, to have with having the right data structures and the functions that will integrate this object into a functional plant. So that's what most of the work requires. And now, just to give an example, if I were to create a storage object, the data provided might look like this. And this would be what AnyLogic would be ingesting. And here we have a scenario ID that specifies what the storage is associated to each scenario, tells me a little bit of what the storage is about, like what does it represent, but also gives me details on the arguments that AnyLogic storage object needs, right? Like number of shelves, number of bays, but also coordinates that are needed for us to initialize this object, right? And on the coordinates, one thing worth mentioning, now this is another piece of the puzzle where we need to think, how do we want to provide a user experience that makes sense? And they can provide us the location of this storages, right, on a layout. So we have been having discussions. There's nothing set on stones at the moment, but we have a couple of different ideas how we could approach this. And but it's still an open topic where we are not entirely 100% in one idea on how a user could set this in the platform. So given that said, that's on the model side, a little bit of a high level overview. Now on the interface, I mentioned that we don't have the platform itself for Eagle Simulate, but this framework has been still used for other use cases, and we have a lot of functionalities that we know it's needed for scenario management, right? So we have this web interface where a user could create a scenario. There are different buttons that we have and functionalities for scenario management. I had to hide some of the information here, but then there are different actions that the user could do. They could view or edit their inputs, and they can click here. And all of this presentation layers built on top of React. And then there is also a way for them to run the model, see the animation in the web platform, but also run multiple applications. They could also delete their scenario. We also have put in place a presentation, the permission layer, where certain users would have higher powers, right, on the interface and be able to do more than just edit a couple of parameters. They would have access to more and all of that. So a lot of this functionality is still going to be needed for the when we have low code platform, right? But we don't have still the part of the puzzle where we need to allow the user to set up locations or coordinates, and how do we handle that? How do we want to do in another page? So that's all is still an open topic. And we also benefit from the private cloud. I've been mentioning bits of it, but the way we embedded our model into this web app is using the API provided. And then we are able to have it, like in the screenshot, just a model in our web app. And also just to give an illustration of the landscape of our user interface, this is pretty much just a high-level picture, but here we have RESTful services that interact with the database. We also have the AnyLogic Cloud API that we use to embed the model in the web app. The web app itself is built using a fast API, and on the presentation layer, we have React. And that's pretty much the current landscape we have for the user interface side. And this is just to give an overview on the Eagle Simulate. Now, how have we been benefiting from all of this work we've been doing on the interface side, like scenario management, and also on the connection, like the bridging of the data with the model, the ingestion. So one of the cases we had that benefited from this framework is this model we built to represent the recycling and casting process. The focus here was to do capacity analysis, but there are more things that this model provides, but the main focus was capacity analysis here. And to give a little bit of context of this operations, the process of recycling aluminum involves collecting and processing different type of aluminum scrap, melting them down in huge pots that we call melter furnaces, and then casting them into new products. And this scrap can be beverage cans to car parts, and recycled aluminum is really present in a really wide range of products we use every day. So there are many different forms and shapes and compositions that this scrap can come from. So the recycling process also from aluminum is very efficient, as this process uses only 5% of the energy that's actually required when you were to produce a new aluminum from raw material. And as an interesting fact, aluminum is also considered an infinitely recyclable material because it can be recycled over and over again without really losing its quality or properties. So this is a very important step of the business in the aluminum industry. which we model by narrowing it down to the remelt process. And the reason why we build it is because, for whom we build it actually. So Novelis is currently building a new plant. So it's still under construction in Bay Minette, Alabama in the States. That is expected to be running by end of 2026. So the operations teams, they have very limited visibility of this non-existing plant. So still on paper, and a lot of the analysis they did are all in Excel-based models that cannot fully capture all of the intricacies of their different furnaces and special furnaces and the interdependencies when they're trying to transfer the molten metal and all of that, so to make a batch of ingots. So also these models didn't offer a good way for them to communicate the results, and were very specific to single users and not so user-friendly in the manner. So kind of a very classic case where simulation could be of help. And we use AnyLogic mainly for 3 reasons. Due to the existing fluid library, but also able to customize with Java code, and also because we're able to provide as a standalone application. So this was the 3 main reasons why AnyLogic was used. And here I couldn't share too much information on the model, so I tried to be very generic. I still give enough information for this presentation, but this illustrates more or less what was done in AnyLogic. So as mentioned, the problem was narrowed down to this piece of the problem, where it's the remelt process of taking in scrap and then melting them down in huge pots and transferring for a holder furnace to be casted. So what happens here is that these melters, melter ABC, they are physically connected with a channel that conveys molten metal into a holder furnace over here. And it could be more holder furnaces, but the role of this furnace is to maintain the temperature, but also homogenize the material, the metal here, until it's ready to be casted into molds. So this is the process, and based on a user-provided schedule, these melters will be using different type of scraps, will be consumed independently by each one of them, taking into consideration the speed of consumption, the desired molten metal composition as well for a specific melter furnace. So once this metal is ready to transfer, then the model would evaluate how much of each one of these pots will be taking to fill up this holder furnace that will be, then this metal will be casted, right? So that's the logic. And we have also considered losses that are called dross losses, which is like as if in when you're cooking, making a soup, and then you have a top that needs to be skimmed. Similarly, in this process, there is a surface that needs to be skimmed, which is called dross loss. And we've been also accounting for those type of metal losses that happens in the process. Now, talking a little bit on the challenges we face. This was relatively small model in scope, and but still had some challenges. One of them I think is worth mentioning is is due to the fluid library. It's a relatively small library compared to the others, and for our use case, needed to have a lot of customization done. And some creative usage of this library to make things possible. And another issue that we faced was handling numeric errors. In the end, we needed to round a lot of numbers to make some condition checks and things to work properly. So that was another thing to handle. And other challenges was mostly related to how do we abstract the logic of how and when to make metal flow from melter furnaces and holder furnaces, but also how to represent scrap consumption and include the concept of different alloy compositions and a specific mix of in a melter furnace I want to achieve. And finally, wrapping up, quickly going over some of the benefits this model provided the team. It was credited mitigation of production loss amounted a little over $3 million. It also now serves the team as a stochastic decision support tool. We made it highly configurable, so a lot of the parameters were exposed for the user to have freedom to change and play with. So they could manipulate different input mixes, different melt rates, play with the changeovers that happen, cycle time, transfer rates, the schedule itself for the line, and other parameters. But also we have provided an easy to manage a scenario management interface. It's for them to quickly build scenarios, but view them. And it also allows the team to easily communicate results. They completely took ownership once this model was provided to them, where they understood the outputs that are provided, and they built their own dashboards, and they build more on top of what we provided. So that was very great to see them taking ownership of this and being able to share also, of course, the analysis done. This tool also now gives them visibility to a plant that is in paper, more than what they had before, which was a static model. So they can establish practices and standards, but also understand the different interactions that would happen between those melter furnaces to make a drop, and how in the end they harmonize and all of that. So they can understand also secondary equipment demand and justify further CapEx investments. That's what I had prepared for this presentation. And now let me have a look if there's any questions. So first question, how many people are working on this and how do you collaborate? So we are a team of 3, but we grew. We have more people on our team. We have one person working on the platform itself, a front-end guy that's dealing with all of this work done with React and Python, Fast API, all of that. But also we have about 3 people working on the modeling side and designing database and all of that. We do all of this collaborative using Git. We pretty much follow Git standards on doing pull requests and asking for revisions, and we have discussions every week on different tasks that were assigned for each other. So that's how we collaborate. And second question, is this library going to have a finite number of operations, or is this library going to be constantly updating infinitely as new operations need to be simulated? And how long does it typically take to create a new operation to add to the library? Is there usually a lot of overlap in logic between the operations? There is a lot of overlap. So it's a finite amount of operations, but there are surely some very different assets. So, but it's finite. So I think that would be the short answer for that. And why did you decide to use the AnyLogic Cloud? Any challenges or disadvantages? AnyLogic Cloud was already something we had previous to me joining, so we just took advantage, and there are definitely benefits of it where you don't have, it's super easy for you to deploy, share models. That's one of them. You have access to the API, so that's really good too. Some disadvantages, I would say there are improvements that could be made on the API. but mostly advantages, I would say, on the cloud. Let me think more. Yeah, big factor is that we have this web platform, and it's really nice to have everything in a single spot where there's no more screens popping up, but it's a very fluid solution, right? Where they just navigate through the web app and everything's there for them to relate it to the model. And did you use any state chart structure for the agents or only the fluid library? For this use case, we only use the fluid library. No state charts for agents, but there was a lot of custom logic created to represent the transferring of the metal, for example, the control of the valves, right, for each one of this, and how do we consume inputs and establish mixes for each one of the melters. So, but no state charts for this one. Will you release this custom library, AnyLogic library, to anybody that wants to use it outside your company? I don't think there's any plans for that as of now. I don't even know how this process would be, but I think the plan is not to. It would be, and it's very specific for the aluminum industry, so I don't think we have any plans. Can this digital twin be embedded in some kind of controller, like Arduino Raspberry Pi for real-time operations control, pulse simulation studies and optimization of parameters? We have not thought of anything like that yet, so I don't have an answer for you on that. Thank you all for the questions.